Privilege to invite Professor Gopal Madabhushi for the next presentation. Um, are you there, sir?
Yes, I am. Can you hear
Okay,
me?
thank you. Thank you. Dr. Gopal Madabhushi is a professor of civil engineering in the University of Cambridge at UK, and he is also presently the director of the Sheffield Center and head of the Geotechnical and Geoenvironmental Group at Cambridge. He has, of course, over 3 decades of he has 3 decades of experience, interest in soil dynamics, earthquake engineering, dynamic centrifugal modeling, FEM analysis, liquefaction, and many similar related things now. But what is most important, interesting for all of us is that he used these principles in biomechanics of hip replacement surgeries and applied the theories of liquefaction and excess power pressure to impaction grafting during revision hip orthoplastics. I think this is going to be wonderful. I mean, using the knowledge he has gathered in centrifuge modeling, FEM, and many other things, actually, he is able to apply these similar principles for our own benefit and more interesting for people, aged people like me, that these are wonderful things. And he was very well recognized for this kind of work also by the Medical Innovation Award. Prof. Madabhushi has also developed numerous equipment at Cambridge University to facilitate study of soil liquefaction, and he was also advising actually the renowned international consultants, that is Matt McNaught, Royal Hoskinick, Ramboll, Whitby. All of them are British origin consultant groups. And then I believe is involved with many studies around the world on post-earthquake reconnaissance. And the two important activities he has carried out, apart from many others, is the analysis of Gigi earthquake in Taiwan and also the Bhuj earthquake, which occurred in 2001, which all of us are familiar with now. He happens to be chairman of the Earthquake Engineering Field Administration team that runs under the auspices of the Institute of Structural Engineers, London. And he also served the BGA as executive committee member from the years 2014 to 16. He has received many awards internationally, but then I'm happy to announce that he also received awards from India, that is by IGS now, the Shamshad Prakash Award, and then the IGS Emil Bainal Award, then IGS ONGC Bainal Award, IGS Professor Shamshad Prakash Bainal Award, and his award actually for the THI Award is even given in 2005, 2010, 2013 by the Institute of Civil Engineers, London. I think this is remarkable that he continues to get it from the same system. Obviously, he's topping and the topic uh, in Britain at least. One of the important things, apart from other applications I want to mention, is that he authored a very successful book on design of pile foundations in liquefiable soils, published by the Imperial College Press, and then the chapters on geotechnical engineering in the book on designing to Eurocode 8, the second edition, published by the Taylor Francis, which is very useful to all of us in India. His textbook on centrifuge modeling for civil engineers was published by Swan Press, Taylor, and Francis Publishing Group in 2014. With his remarkable achievements in the area of general geotechnical engineering and soil dynamics, and its application, relevant application to Indian and other issues around the world, it's my great pleasure to invite Professor Gopal Madabhushi for his keynote lecture on solutions for foundation systems related to earthquake conditions. Thank you, Professor Madabhushi. Hello.
Yeah, I can.
Over to you, Professor Madabhushi.
I'm trying to share my screen.
Okay, please go ahead.
Can people see my screen?
Yeah, now we can see it. Perfect.
Fantastic. Okay, thank you very much, Professor J.V. Rao, for that very kind introduction. I hope I deserve at least some of the praise you heaped on me.
You deserve much more than this. I was very brief, actually.
It's a real pleasure to be a part of the IGC conference. It would have been great to meet you all in Vizag, one of my favorite cities. It has mountains, it has beach, two of my favorite things. I hail from Kakinada next door, which has the beach, but no mountains, I'm afraid. So I always was very attracted to Vizag. It's a pity we are going through such a difficult time everywhere around the world. So I can't be there, but at least I can do my presentation online. So today's topic I chose was sustainable measures for protection of structures against earthquake-induced liquefaction. As you all know, sustainability has become quite important, and world is waking up to various risks of endlessly using its resources without any consideration for how sustainable methods of usage are. So soil liquefaction is particularly difficult. Here are some examples from different earthquakes where buildings either settle into the ground because the ground has liquefied, or they rotate as the soil below the foundations starts to liquefy. Of course, it's not going to sustain the vertical pressures applied by the foundations. Therefore, they try to sink or rotate.
Sir, can you be near the mic?
Yeah, sure.
Yeah, now it's better. Yeah.
Here is a picture of large-scale damage that has happened in the Palu earthquake in Indonesia in 2018. And this all happened. If you see, the structures are quite small. They're just residential structures. And they got wiped out. Here is a little video. I hope you can see this, where the ground started to liquefy and flows like almost like a river, destroying all the houses. So the picture we saw before is what has happened because of this widespread lateral spreading following liquefaction. It's quite amazing. These are just a series of satellite images that got stitched in to make it look like a video. But you can see once the ground liquefies, it basically flows like a river. Now, I don't know if, in case you couldn't see the video, I also had a still picture of before and after here. And you can see it's completely, all the houses got destroyed and it all turned into basically you can see the soil now. Now, in order to prevent damage from liquefaction, the currently available methods are either you densify the soil, you improve the drainage. Dewatering is a solution, but not often practical because if the water table is quite shallow, you can't remove all the water. Grouting and reinforcement, of course, these are hard engineering solutions. What we want to look at is, so these are the methods available. So you improve the ground below the foundations, either by densifying or putting drains into them. So I'm going to focus today on the drainage. And this work was carried out by my current PhD student, Sammy Garcia. She's from Peru. And she's done a fantastic job, and I'll share some of her results with you. So what we're looking for is drainage using vertical drains as a countermeasure for liquefaction so that we can get rid of the poor pressures that are generated in the ground due to shaking. Now, these are normally carried out, this is a fairly simple solution where you make lots and lots of drains into the ground. And here are some pictures of improved ground by putting drains into it with coarser materials like stone columns are one option, or you can have more specific earthquake drains as well. Now, with the improvements in the directional drilling, we can put vertical drains around the ground, and also some incline. If you want, if you have the building already present, you can also place drains in an inclined fashion as shown in this slide. I'm going to focus on the vertical drains for the purpose of this presentation, but we also carried out some tests on the inclined drains. The main focus has been to try and use some recycled materials. For example, gravel is traditionally used for stone columns. Also, there was some research carried out by my good friend Hazarika from Kyushu University, who are looking at old tire chips to use in the drains. So we wanted to evaluate using dynamic centrifuge and numerical modeling how the drains actually function, particularly in the presence of foundation. So firstly, to introduce you, we have this large centrifuge facility, and I've shown this many times in previous IGC conferences, and it's able to go up to 100 and 50G and can carry about a ton of payload. We have a similar facility in Bombay as well, which Professor Chandrasekharan has developed over many years. Now, to do the earthquake modeling, we do, in addition to having this normal gravity, the earthquake events are mimicked by applying large lateral accelerations. To do that, you need powerful earthquake actuators that can shake the models in flight while the thing is spinning around at about 150 RPM at 200 miles an hour. So that's not easy. Earthquake accelerations, one must remember, have to be generated normal to the centrifugal acceleration. There are a set of scaling laws which link what you observe in the model to what happens in the prototype, and n is the scaling factor you might call. The current earthquake actuator we are using is the servo-hydraulic earthquake actuator, and this is able to model any previous earthquake or motion or any other motion you desire. You just need to program it into the shaker first, and it will repeat it. Here are examples of the Kobe motion and imperial motion that we simulated at about 60G. You also need some specialist containers like the lamina box so that the boundary effects are minimized. And the lamina box we have simulates something like a 40-meter long soil model, which is 20 meters deep. So you can study really deep models of soil and see how it liquefies using instrumentation. Coming back to the drains, this is the most arduous part of the modeling. You need to create these models at small scale. So here is Sammy having a go at constructing different types of drains and then placing a foundation block, as in number 3 here, on the surface, which can apply 50 kilopascals of bearing pressure onto the soil. In addition to the vertical drains, we also managed to make these inclined drains. As you can see, here is the form work that she very carefully placed beforehand, and then the completed version of the drains post-construction. So she became quite adept at making small-scale models in doing this. So the 3 types of materials we chose for in this modeling. The first is the Houston sand, which is the liquefiable sand, which forms the bulk of the material. And the drains were modeled either using what we call fraction B sand, which is a coarse sand, or rubble brick. We wanted to use the rubble brick so that you can use construction debris or other construction waste materials in a sustainable fashion to make these drains and prevent large-scale liquefaction. So we want to study whether this works or not. Here are some grading curves just to show that the soil we chose liquefies, but the drain material actually satisfies both the anti-clogging criteria and is also able to have high permeability so that you can conduct the excess pore pressures quickly. There are a few terms you need to be aware of in terms of this modeling. For example, flow front, that is the time it takes for this ground to start draining post-earthquake. Unit cell is a cell that is formed around each drain into which the fluid will flow, and infinite cell is where the drain is getting fluid from all of the liquefied soil in the absence of any adjacent drains. So, as I said, vertical drains are commonly used in many places, but the design is all driven by on the assumption that there are no structures in place. And this has been developed by Seed and Booker many years ago, and that's largely used with some minor modifications. But of course, this is very unreal context for how you should be designing them, because you will have structures in place, and you need to see how these drains perform in the presence of the structure. And this is what we did for the first time. So coming back to the modeling aspects, here are some cross-sectional drawings where you can see the drains being placed underneath in the sectional view and also in the plan view. And we modeled various foundations with 50 kilopascals to 150 kilopascals. And because we have instrumentation buried in there, you can monitor the excess pore pressures that are developed. and you normalize them with the vertical effective stress, and you define what is called excess pore pressure ratio. If you got an excess pore pressure ratio of 1, basically you completely liquefied the soil, and if it is lower than that, it is good. And 0 means no liquefaction. So once we apply some sinusoidal motion of shaking like this, we can monitor the pore water pressures at different elevations below the model. But the interesting thing is you can construct these contours, and you can see what is the pore pressure ratio value, excess pore pressure ratio value below the foundation. And in the improved zone, you can see below the foundation where the drains are, you're getting blue, which suggests that there is no excess pore pressure, not much excess pore pressure. Whereas as you go outwards, obviously your free field is completely liquefied. This shows how well it liquefies, and also because we're monitoring with time, you can see at different time intervals at the end of the earthquake, some time after the earthquake, and much longer after the earthquake, how the water pressures are changing. So eventually everything will turn blue. So orange is bad, blue is good. You can also construct the contours in taking the vertical section, and you can see below the foundation you're getting blue, which means that you prevented liquefaction there, whereas the free field is liquefying initially. And as time passes, everything again turns blue. So this is quite interesting to look at. You must also look at what horizontal accelerations are propagating through the ground. Once the ground liquefies, obviously it isolates and not much shear stresses go through it. And you can see if I'm applying a 10 cycle sine wave roughly at the base, in the free field, it completely, there is no transmission of the accelerations. In the improved zone, there is also isolation, but the accelerations peaks are a bit larger. And again, in the unimproved region, they are smaller. So this suggests that if you improve the ground, you will transmit more accelerations, and that's an inevitable consequence of preventing liquefaction. You can't have it both ways. But most important design criteria is the settlement of the foundation. And you can see compared to the free field, the foundation will always settle more. In the unimproved zone, it settles something like 600 millimeters. But with the improvement, it has come down to 400 millimeters for this particular configuration of the drains. We also monitor the horizontal accelerations received by the foundation itself. If you improve the number of drains, we looked at 13 and 17 drain configurations. How much improvement do you get in terms of settlement performance? That's the criteria. Of course, we can look at these pore pressures again, and you can see with more drains, you are getting less of an RU and so on. But and you can see that the dissipation patterns of the excess pore pressures are pretty similar for both 13 and 17 drain configurations. The improvement below the foundation is a bit better with the 17 drains configuration immediately at the end of the shaking, which is the important thing we want. But again, the accelerations are transmitted as you expect with a reduced amplification. But the most important result here is the settlement has reduced from something like 400 millimeters for 13 drain configuration to 250 millimeters settlement with the 17 drain configuration. One of the things we observed was that these drains are getting bulged on the top under the foundation. For example, schematically, you can see that because of the vertical pressure exerted by the foundation, the drain itself will lose it'll lose its shape in the top meter or 2 meters height. And that will cause additional settlements because the drains are not supporting once the soil liquefies the foundation. And you can improve this by having the confinement. I'll come to that in a second. One thing we can look at is the rotation. The settlement criteria I compared before, 400 to 250, that's an improvement. But you can also look at the rotation response of the foundation. You don't want too much rotation response either. And that again is plotted here. If you can encase the drains on the top 2 meters depth, we saw much improved performance. Here is the pore pressure contours I was talking about earlier. When we encase these drains with stiff material like a perforated tube, then you can see the liquefaction happens a lot more around the drains, because it's you effectively reduce the permeability of it, but the settlement has reduced much even better than even compared to the 17 drain arrangement. And that's really a big point we can take into design. When you make these stone columns, it's better to protect them for the top 2 meters or so using these encasing of kinds. So centrifuge modeling can give you other ideas on how to improve your design parameters. I briefly want to talk about some of the 3D finite element analysis we have done using Abacus and CAE platform. The analysis have to be in 3D because drainage and drains are 3D. And we had a complicated procedure of setting this up. I must emphasize here, we were not trying to model the generation of the pore pressure part itself. For that, you need really sophisticated constitutive models, and Abacus itself can't do it. But the dissipation part, it can do quite well. So we decided to use the 3D capabilities of Abacus, but with some assumptions on the top, saying that we know, if we know the pore water pressure, how quickly will the drains actually come into action? So we had a few steps to get to there. We made our 3D model and the foundation on the top. And the settlement matching is what we were looking at. So in the bottom picture here, you can see that we could get quite a good match between the numerically predicted settlement compared with our own centrifuge result. And we've done this for different configurations. Obviously, here is the 13 drain configuration I was talking about earlier. And we can look at the pore water pressures and how long they're taking to dissipate in the 3D model compared to the numerical model. At some locations, it's pretty good. Where the perimeter drains are there, it's pretty good. In the closer to the drains, it's not so good. And sub-perimeter drains, it's also not, it's reasonable, but not great. So you can then construct the same contours and compare what we were seeing in the centrifuge, which is really physical data, to the numerical analysis. Broadly, it matches well, but again, at the end of something like 180 odd seconds, you can see it helped the excess pore pressures are completely dissipated. While we are matching the settlement quite well. So we were kind of concentrating on, can we predict the settlement correctly or not? With that, I'd like to come to my conclusions. Now, soil liquefaction can be very widespread, as illustrated in the Palu earthquake at the beginning. There are many small to medium-rise buildings which need really economical and sustainable methods to prevent liquefaction damage. It's not, you cannot use pile foundations for everything to try and protect them, because the building cost compared to the foundation cost should be reasonable. You cannot make foundations which like you would do for, say, a multi-million-dollar high-rise building for a small house. That just doesn't work. We could, you get a lot of construction debris coming out from the construction industry, and we mimicked this using rubble break and see how we can mitigate earthquake liquefaction risk. Now, extensive centrifuge testing has demonstrated that these excess pore pressure variations close to the drains, we are actually looking at the mechanics of this and how the settlement, corresponding settlement happens when the buildings are suffering settlements. And we could show that the rubble brick drains can reduce settlement significantly. And we were able to capture this using simplified 3D analysis, so that the main idea is that, can we provide the designers an easy method so that they can use sustainable materials in their design to make these drains, and at the same time be able to make satisfactory predictions to estimate the settlement of the building using some standard finite element package like Abacus. We used Abacus, but I'm sure you can do this with any other 3D finite element package as well. It's the procedure that's important. I'd like to conclude by acknowledging a few people. My student obviously wants to thank the Peruvian Science and Technology Council for providing her funding. We'd like to thank, both of us like to thank our technician staff at the Scofield Center who helped us make these complex models, the Department of Engineering and colleagues there, and the Murray Edwards College, to which Simon belongs. Thank you very much.